The universe is dying, but its final chapter belongs to those who refuse to go out. Long after the last star burns out, the universe will go dark. But it does not have to go silent. Any civilization still alive in that distant future could survive by turning black holes into the ultimate power plants. Right now, we live in the Stelliferous Era, the brief age of stars. But according to the Lambda CDM model, our universe is being driven apart by dark energy, a mysterious force making the expansion of space accelerate faster and faster without end. That expansion feeds a relentless process entropy. Cosmic disorder must always grow, pulling every organized cluster apart into chaos. In 100 trillion years, the final stars exhaust their fuel, and the universe enters the Big Freeze, a state of total frozen stagnation. Once the starlight is gone, the cosmos becomes too cold to do any useful work. For life, survival becomes a single question. Where do you find energy when none seems to exist? In 1852, the physicist Lord Kelvin applied the laws of thermodynamics to the entire cosmos. He predicted a final heat death, a state where all energy is spread out perfectly evenly and motion stops forever. More than a century later, the data agreed. By measuring the cosmic microwave background, the WMAP satellite confirmed our universe's density is low enough to expand and cool forever, exactly as Kelvin foresaw. But while the stars go out, they leave something behind: the most concentrated energy reserves in the universe, black holes. As the lights fade, we enter the black hole era. Starlight becomes a memory, and intelligent life must adapt to a stark, dark reality. To survive, a civilization must exploit a strange property of black hole physics. These objects have their own temperature and their own entropy, and mass determines temperature in reverse. A microscopic black hole is blisteringly hot and radiant. A supermassive one sits just a fraction of a degree above absolute zero. A black hole economy would cultivate that difference. Small, hot black holes provide immediate power. Supermassive ones serve as cold reservoirs to dump waste heat. By running between the two extremes, a civilization could drive a heat engine and keep doing work in a dead universe. It would build a colossal Carnot engine, running between a hot black hole and a cold one. Radiation from the hot source flows into a cylinder. Its pressure pushes a piston outward, doing useful work as it expands. The cylinder seals. The radiation keeps expanding and cooling until it matches the freezing environment of the larger black hole. Then the cylinder opens to the cold side. The piston pushes the spent radiation in, and the cycle resets, ready for the next round of power. If those two black holes ever merge, the energy the engine extracted equals the mass lost between them. Power, drawn from pure darkness, while the total entropy of the universe stays constant. But even this has a limit. The quantum nature of black holes guarantees that even these batteries eventually run dry. As Stephen Hawking famously showed, black holes are not permanent. Through Hawking radiation, they slowly leak their mass and energy back into space. For a supermassive black hole, that decay is almost unimaginably slow, perhaps 10 to the 100th power years. In its final moment, the black hole evaporates in a sudden burst of high-energy photons, leaving nothing but empty vacuum. When the last black hole dies, the last heat engine stops, and the universe's final fuel is spent. This is the dark era. The cosmos thins to a dilute haze of photons and leptons, hovering a hair above absolute zero. Thermodynamic equilibrium. The true heat-death energy spread evenly across a boundless void, where biological life is a physical impossibility. Our star-filled age is a microscopic sliver on this timeline. It is the era of black holes that defines the true lifespan of our universe. Heat death is an inescapable certainty. But the physics of black holes extends the possibility of life and intelligence by trillions upon trillions of years, reframing the whole cosmos as one grand, deep time story of survival.